134 molars potassium permanganate for its titration in an acidic solution.
Okay. So 250 milliliters of saturated calcium sulfate, calcium oxalate requires 0.0, what was it again?
0.00134 molars.
How many milliliters?
4.8 milliliters.
4.8
Milliliters.
milliliters, okay.
So, what is the value of KSP for the calcium oxalate
Okay.
obtained with these data?
Well, for calcium oxalate, CaC2O4 solid, we first can generate the KSP equation, calcium 2 plus C2O4 2 minus, here. In order to figure out the KSP from experimental data, then we just need the equilibrium calcium concentration and the equilibrium oxalate concentration.
So it also says in the titration reaction, oxalate ion is oxidized to CO2 and permanganate is reduced to Mn2O4.
Okay. All right, so normally we just start off with 0, 0, and then the change. At equilibrium, we're going to have S molar and S molar here. But no, the normal way we do things is we're given a KSP value, and then we figure out what S is, the solubility, or figure out what the equilibrium concentrations are. And this one, what we're going to do is we're going to figure out this, S molar. The S molar, this we're going to get from titration data. So we'll get the oxalate concentration here. The reason we can get that is because from this, if we have the volume and the molarity, then we can get the moles of KMnO4. And from the moles of KMnO4, we have a reaction with oxalate. And so what we'll do is we'll get the moles of calcium oxalate. And from the volume, we have 0.250 liters. We'll get the molarity because the volume is equal to 0.250 liters. We'll get the molarity. Once we have the molarity of calcium oxalate, that's the equilibrium molarity. That's because what we have here is a saturated solution. So saturated solution is we start off with pure water and then dissolve as much calcium oxalate as we can, and that's what we get here, S molar for the solubility. And so here, it's just liters. We'll go to 0.00480 liters times 0.0134 moles per liter. That gives us moles of KMnO4. Now, this one, what we need is we need the balanced chemical equation for this. And so this is not an acid-base titration. This is a redox titration. So the different indicators that we use, but essentially it's the same thing. We have some indicator to tell us, the right amount of KMnO4 to add to this. In other words, the equivalence point. And so we have to generate the equation for this first. And so the reaction here is KMnO4 plus calcium oxalate. This looks like a metathesis reaction, right? But when we come up with it, it's calcium permanganate and potassium oxalate. There's no reaction for metathesis. For bronzite acid base, it doesn't look like much. Oxalate is dibasic base, so we hydrolyze water. Should be the strongest base around. So, but there is a redox reaction that occurs to this. And we should have suspected a redox reaction because potassium permanganate is a powerful oxidizer. In fact, when you look on the chart here, it's number 3 on the chart. There's fluorine, hydrogen peroxide, and then permanganate. But we need acid solution. The problem is that there's already acid present, so we don't have to worry about this plus 80 pluses because it's already present. And so all we can do, here we could save a little bit of time just by writing it down off the chart. that is permanganate plus 8H plus 5 electrons yields Mn2 plus 4H2O liquid. And so this is one half reaction, and so we have a powerful oxidizer here. So what's our reducing agent? So if that's our oxidizing agent, then our reducing agent's oxalate. The calcium ions and the potassium ions are going to be spectators. We don't really have to put that in there. So let's just go ahead with the oxalate. The oxalate, when it's oxidized, what does it form? Carbon dioxide. That's complete oxidation of oxalate. Let's see if we've got an internet connection. Yeah. So, oxidize it to CO2 gas. Okay, this one is not on the chart. And so this one we have to use some Chem 1A.
This is also called skeleton.
This is skeleton redox. And so for oxalate, we have 2 carbons here. We'll need 2 CO2s. Balance out the oxygens. The oxygens are balanced. The hydrogens are balanced. The only thing left are the electrons are charged. And so then that would be balanced here.
And we have to multiply the equation by 5 and 2.
Yeah. Right. And so this one will multiply by 2 here. And this one will multiply by 5 here. And so the ratio between permanganate and oxalate is it's going to be 5 moles of oxalate for every 2 moles of permanganate. And so this will allow us to do our mole-to-mole conversion. We'll go from moles of permanganate to moles of oxalate. And then from moles of oxalate, that's what we want. We just leave it there and just divide it by 0.250 liters. Gives us our molarity. Once we know the molarity of oxalate, then the molarity of calcium is the same, so we just square it. Or just multiply it by 2. I mean, not 2, but multiply it by itself. Okay, it's back. All right. Is that enough?
Yeah, that's enough to get started. We also do 14.
14.
Because when I did the math, it got, for the KSP, I got 8.3 times 10 to the negative 17. I don't know if that's too small.
10 to the negative 17 is okay. When you look at the KSP value, that's kind of in the middle. And so it wouldn't be too small. There are smaller KSPs, like 10 to the minus 51. But we can take a look at the math there and just double check that real quick. Unless, did somebody else get that? Let's see. What number was it again?
14.
14. All right, 14 says this: excess calcium hydroxide is shaken with water to produce a saturated solution. And so we're going to have a saturated solution of calcium hydroxide. Saturated solution of calcium hydroxide. That just means QSP is equal to KSP in this case. And we just have the right concentration of ions to it. Any more and it'll start to precipitate, any less and it'll be unsaturated. A 50 milliliter sample of the clear saturated solution is withdrawn and requires 10.7 milliliters of 0.1032 molar HCl for its titration. What is the KSP for calcium hydroxide? So this is just, how do you measure the concentration? And so here, if we have calcium hydroxide and we saturate the solution, we have some solid here. We're going to form some calcium 2 plus and 2 hydroxide. And so there's nothing there, it's just water, and then the change will saturate it, so we'll get S molar and 2S molar here. Now, the situation, how do we measure this. You know, we could calculate it if we had the KSP, but in this case, we don't have the KSP. The KSP is unknown. And so how do we measure it? There are different ways. We have to take advantage of the chemical properties of these things. So if we have hydroxide there, then we can just do a straight titration.
I did, since for HCl they gave us the molarity of the volume,
Yeah.
I calculated the molarity, like dilution molarity.
Okay, solution dilution.
So then I got for HCl, the concentration is 0.01809 molarity. And then, for calcium, hydroxide, I said like Z is the molarity we're looking for.
Okay.
And then I started going to, well, how am I gonna find OH? So then I used water. And
Okay.
then started doing KW.
We don't want to go KW here.
Okay, that's what I figured.
All right, let's see where you're at here. So we had a 50 milliliter sample. This is the original sample. In this 50.0 milliliter original sample, this is what we have for the concentrations. It should be S molar in 2S molar from that. All right, so this is saturated, and it's the same thing here. So, you know, maybe there's 300 milliliters, you take 50 milliliters of that. All right, then what they're going to do is they're going to do titration. A titration to analyze the concentration of hydroxide here. And so the concentration of hydroxide is 2S molar here. The concentration of calcium is S molar. All right, so if we do the titration, then the titration here, we're going to add plus how many mils? 10.7 mils, 10.7 milliliters of 1032 molar HCl. All right, so there are actually different ways we could do this. You know, this particular calculation. One of the ways we could do this is like this. We could go from here, we could go to moles of HCl. From moles of HCl, we could go to moles of hydroxide. And from moles of hydroxide, we can go to molarity of hydroxide. But this is tricky because which volume do we use? Do we use the 50 or do we use the 10.7 plus the 50 or 60.7? And so this one, we can get the molarity of hydroxide by dividing it by the original volume. That is 50 milliliters. Because all the hydroxide came from this sample. So that's one way. Alternatively, we could do what you did. We could do a solution dilution. And so if we do a solution dilution, this is what we're going to get. We're going to get 60.7 milliliters of total solution, 60.7 milliliters. And what we're going to have here is this. Sorry. What we're going to have is this. The concentration of hydroxide here. Did it stop?
Yeah.
Gosh. The concentration of hydroxide is here. So this is the original. We'll call it original. This is the original. Then we have this hydroxide here. And so what we're going to do is we're going to do a solution dilution. That is, the hydroxide is going to be 50.0 divided by 60.7 dilution factor times the original concentration. The original concentration of hydroxide is 2S molar. And then we can figure out the new concentration of calcium. New concentration of calcium is going to be a 10 point, oh, what is it?
10.7.
No, I'm sorry, 50.0 over 60.7 times S. That's calcium. And then we need the HCl concentration. The HCl concentration is going to be a 10.7 to 60.7 dilution point 1032 molar. So this one we could solve here. So if we wanted to do this like a chapter 17 problem, we would be doing it like this. And then we're going to have a problem because we take the strongest acid, HCl, and react it with the strongest base. The strongest base is just going to be hydroxide. And this is going to produce water, H2O liquid. K for this should be very, very, very large. And so it's going to react to completion. And so what is the HCl concentration here?
Zero point 01139.
And so initially we're going to have 0.01139. All right, now the hydroxide ion concentration is 50.0 divided by 60.7 times 2S. That's going to be the hydroxide ion concentration that we figured over there. And then this will be liquid, pure liquid. Now, titrations, we add the stoichiometric equivalent, right, of base in this case, or we add the stoichiometric equivalent of acid. And so in titration reactions are stoichiometric. You know, we want to hit the end point, which should be very close to the equivalence point. You know, hopefully they're the same thing, the equivalence point and the end point. The equivalence point is when we have equal amounts of reactant. And so what we have to do is we're going to say we hit the equivalence point here. If we hit the equivalence point, then we should have neutralized all the acid and all the base. So we end up with 0 and 0. Because K for this is very, very, very large. And so that means this. That means this must be minus 0.01139 molar, and this must be minus 0.01139 molar here. And so, in other words, this 50.0 divided by 60.7 times 2S must equal 0.01139 molar. You know, because we have to have 0.01139 because we're subtracting that and it's got to equal 0. And so we'll start off with 0.01139 minus 0.01139, and we end up with 0.
So then I have S is equal to 0.00.
Yeah.
6914.
Yeah, okay. And so we could plug that in here. That would be the original calcium concentration. So you plug that in. What was it again?
0.0069144.
Okay, that's the calcium concentration, and double that for the
0.013828.
okay, and then just multiply those together. And what do we get?
9.56 times 10 to the negative 5.
right, that should be based on the, so this is a saturated solution. Based on this saturated solution, those are the concentrations we have in the original. 9.56 times 10 to the minus 5.
Now, we could just do a quick check to see, you know, if that looks good. By looking at the KSP for calcium oxide, or calcium hydroxide.
It's 4 times 10 to the negative 9.
4 times 10 to the negative 9 is the KSP?
Not correct.
Yeah, KSP equals 4 times 10 to the negative 9. That's way off.
Way off. And so what should we do? Well, first we should see, did we make an error someplace? And so go back through it and see if you can find some kind of error. Oh, that's the book's answer? What was the book's answer?
Oh, I have no idea.
Oh, that's what you got, 10 to the negative 9? Well, look at what calcium hydroxide should be. According to this, calcium hydroxide should be 5.5 times 10 to the minus 6. 5.5
times 10 to the minus 6. This is still way off. You know? So let's think about it.
Oh, wait, but that equation is for calcium oxalate. That KSP formula we just used.
Oh, what's that?
That KSP equation is for calcium oxalate. So calcium hydroxide is 5.5 times 10 to the negative 6.
Oh. All right.
So it was right.
What are we doing? Yeah. I guess I didn't erase this, huh? All right. I didn't erase that, did I? And so that was a mistake then. So KSP is going to be S times 2S quantity squared. And so did you plug those in?
S is still equal to the value that we put in, right? 0.0069144.
Yeah. Well, let's, we can calculate it right here.
$1.3 times 10 to the negative 6.
1.3 times 10 to the negative 6, is that what you get? Okay, 1.3 times 10 to the negative 6. What do you think? Are we close? Would you consider that close, or are we still far off? Now, if this were chapter 16, chapter 17, I'd say we're pretty far off. But this is chapter 18, and what are we factoring into consideration?
Common
Hmm?
ion? Common ion?
Not the common ion effect. We don't have common ion.
Well, I didn't factor in the dilution factor.
The dilution factor, we already factored that out because we're calculating the original
Oh.
here. So even though it's off, you know, what is it, 1.3 times 10 minus 6? Even though it's off, we might say, okay, this is okay because we aren't factoring in things like what?
I have a question. Is there a multiplication error in the HCL?
I don't know, is there? Let's see. No, let's check. Let's double check our calcs.
0.01849.
Yeah, that's what I got too.
But if I follow the calculations all the way through, I get 5.382 times 10 to the negative 6.
5.382 times 10 to the negative 6?
Yeah, but
5.38 is getting closer. 5.5. And so this is calculation error? Oh yeah, there is one. This one I get, what did you get here? 0.01819?
yeah.
Yeah.
Point 01819, the HCl. So that's got to go over here, times 60.7, divided by 50, 0.02208. Which is going to equal the hydroxide ion concentration. The hydroxide ion concentration is equal to 2S, and then we'll take that in half. That's going to equal the calcium concentration. So let's double that. And so I'll take this and square it. So this is going to equal 0.01104 times 0.02208 squared. So I'll square this. Divide times 0.01104 equals, yeah, 5.38 times 10 to the negative 6. How does that look compared to that? Good? All right, so that's closer, 5.4 versus 5.5. So, you know, and let me get back. Why, you know, if your calculation's off a bit, why might we expect the calculations to be off a little bit? Not a huge amount, but, or maybe it might be a huge amount. It's tricky. You know, it could be up to 25 times off. Why? Not common ion effect.
No ideas? Did you guys review the notes for the topics? We did talk about limitations of KSP, did we? Is it in your notes? Hopefully by the time the test comes, you know, because we covered limitations of KSP last week. What day was that? Wednesday? Maybe? Wednesday last week. Hopefully by today you would have seen it at least 5 times or something, you know? Just,
Did we use the activities?
because of activities, right? We should be using activities. Should be activities. Activities because of what?
Because it's more, doing stoichiometric is more ideal in how it actually reacts. When you use activities, you can show you how the items would actually react to the solution.
Yeah, and the activities, we should be using activities because of why do we use activities? To compensate for interionic attractions, right? Ion pairing. And so in this case, do you expect ion pairing to be significant or not so significant? Significant. I mean, calcium is a 2+ ion, right? And so you have something like that. Anyway, this is what we got here.
So when you did the math, it came out to 5.38 times 10 to the negative 6?
Yeah, 5.38 times 10 to the negative 6. So double check your calculation. So let's see. It goes from there. All right, other questions? What time is it? No?
Exercise 18.8B.
Exercise what?
18.8.
18.8B. Let's take a look at that and then.
Page 798.
798. (18.8B). All right. Will a precipitate of iron 3 hydroxide form from a solution that is 0.013 molar iron 3 plus in a buffer solution that is 0.150 molar acetic acid and 0.250 molar sodium acetate? This is a composite problem. This is a problem with chapter 17 and chapter 18 material together. I'm not going to give you those types of problems most likely. I'm just going to stick with chapter 18 material, and that's it. But to figure this out, this is, will it precipitate? And so what we need to do is a QSP type problem. So if we have iron 3 hydroxide solid, this is going to form iron 3 plus and 3 hydroxides here. So initially, well, actually, we don't know because we don't have to do the solubility for this just yet. What we can do is we can just do QSP. You know, compare QSP versus KSP and then see. Well, what is KSP? Well, KSP is just going to equal. We have to look that up. Is it given in this problem? Let's see. Okay. Let's go back to
4 times 10 to the negative 38.
4 times 10 to the negative 38.
Yes.
Okay, then we look at the QSP. The QSP is going to just be the given concentrations. So this would be iron 3 plus concentration initial times the hydroxide concentration initial cubed. And so the iron 3 plus concentration they give us here as 0.013 molar.
And so initially we're at 0.013 molar. And so we're going to see, is this going to shift left or shift right, this equilibrium? And then the hydroxide ion concentration initial. Well, the initial hydroxide, it's going to come from the buffer solution. And so what we have is a base to acid ratio of 0.250. So this is going to be from the buffer. And so why don't you calculate the pH? The pH is going to equal 4.74, this is the pKa, plus the log of the base to acid ratio. The base, 0.250, the acid, 0.150. And so what does that give us for our pH?
$4.96.
4.96. Okay, that means if we get a pH of 4.96, we can get the POH. The POH is going to be 9.04, and that means the hydroxide ion concentration is going to be 10 to the minus 9.04, which is equal to what?
9.12 times 10 to the negative 10.
It's 10 to the negative 10. And so what we're doing here is we're going to plug that in here, 9.12 times 10 to the negative 10 molar. And we're going to see, we have three choices for the change. This is going to shift left, that is, this will be minus x, minus 3x. Or it's going to shift right, plus x, plus 3x. Or there's going to be no shift because it's already at equilibrium. It's already saturated. And the way we can figure out the direction, I don't bother doing Q calculations because what I do is I just reset this. Because doing that extra Q calculation is not necessary for most problems, because most problems we just want what we have at equilibrium. But for this problem, we need to do it. We need to see, is this going to shift left or shift right or no change? And so in order to do that, we calculate Q, we'll plug that in here, 9.21 times 10 minus 10 cubed times 0.013. And does it come out greater than, equal to, or less than 4 times 10 to the negative 38? So can you calculate that and see? Right back. 9.86 times 10 to the negative 3, which means what?
It's bigger, so. I thought it shifts to the right.
Q is
Oh, Q is.
K is right, Q is left.
No, but if the Q value is greater, then does the reaction occur or does the reaction not occur? I thought if the Q value is greater, it shifts to the right because it continues. Right. Open it, you open something.
So QSP came out greater than KSP, therefore what?
Shifts to the right.
If QSP is greater than KSP, we have too much product. That is, this is top heavy, the numerator is too big, which means it's got to shift not to the right, to the left, to make it a smaller number. Right now the ratio is too big, too much product. And so do we get a precipitate? Yes, it will precipitate. Yeah. I mean, there's too much here.
Oh, okay.
It's going to shift. I wouldn't, you know, this is called the Le Chatelier shift. I did this in chapter 16. I wouldn't solve it as a Le Chatelier shift problem. What I would do is I would reset this and do it that way. We could find out how much precipitates by comparing, you know, this initial with the equilibrium amount. Once we know what the equilibrium concentration is, then we can get what's called the percent remaining. And from the percent remaining, we can get the percent precipitation. But even more than this, we can get the grams. How many grams will precipitate from this, you know, by doing this calculation. And so this is why I wouldn't calculate Q. I wouldn't calculate Q because it's going to look bad, the math. Because if we calculate Q and say, okay, it shifts to the left, then we're going to get 0.013 minus x, and then we're going to get 9.12 times 10 to the minus 10 minus 3x. And then we plug that in here for a KSP. And so the KSP is going to equal the iron concentration, 0.013 minus x, times the hydroxide ion concentration, 9.12 times 10 to the minus 10 minus 3x, quantity Q. Does that math look good to you? No, this math looks awful. And so rather than doing this, we would reset it. Now, resetting this, which one's the limiting reagent? The hydroxide is the limiting reagent, so we get a new initial conditions. The new initial conditions will be this. The hydroxide will go down to 0 molar. We'll call this minus 3y. And this will be minus y. And so minus y would be 1/3 of this. And so what would that be? That would be 9.12 times 10 minus 10. Okay, and then subtract that from 0.013. So we'll go 0.013 minus 3.04 times 10 to the minus 10. And so that's going to come out to, yeah. Basically, it's going to come out to 0.013. You know, doesn't really change it. It's such a small amount. All right, now we do the change. Now the change is going to go to the right, so it's going to dissolve. So this is going to be plus S plus 3S. And so at equilibrium, we're going to have 0.013 plus S molar and then 3S molar here. And so the KSP, rather than having this expression here, we're going to have this one. This is going to be 0.013 plus S times 3S quantity cubed. Now this looks a lot easier, I think. But there's one other advantage we have, and the other advantage is that, what was the KSP again for this?
4 times 10 to the negative 38.
38? What does that tell you? Are we going to dissolve very much?
No.
No, and so that means the simplifying assumption should work. So we use the SA, we're going to get 0.013 times 3S quantity cubed. And then we'll solve for S. And so I'll just do that on my calculator here. I'm getting 4 times 10 to the negative 38 divided by 0.013 divided by 27, and then we'll take the cube root of that. .85 times 10 to the minus 13 times 10 to the minus 13. And so 0.013 plus S is going to be about 0.013. And then over here, this is going to be about 4.85 times 10 to the minus 13 times 3. It's go ahead and times this by 3. Times 3 equals 1.45 times 10 to the minus 3, 6, 9, 12. Times 10 to the minus 12 molar. All right, let's check the K value. And so I'm going to do that times 0.013. See if it works. Oops, I forgot to cube it. So let's clear that times 1, and then I'm going to cube it times 0.013. I get K is equal to 4 times 10 to the negative 38, which is good. So, in this particular problem,
I just thought, so like, if you look at the example 18.8, it says, in the analysis, the key here is understanding that hydroxide ion is established by the ionization of NH3. So I assumed, like I had to convert the acetic acid, and then the NaH2C3 of H, no, C, you know what I mean? I thought like I had to use ionization for that, but I guess not.
No, because this is a buffer solution. If this were, okay, they wouldn't put it together. If this were just this, then you'd have to do KB to figure out how much. But since it's a buffer solution, we could use the Henderson-Hausbach to figure out how much hydroxide. And so it makes it a little easier. And so basically, this is what's going to happen. We start off with this. The buffer solution will maintain, you know, and so this is what we're going to get, but then it's going to redo it. And so actually, the buffers, that makes it even trickier. Shoot. A buffer solution. What does a buffer mean? A buffer solution means this. This is for initial concentration of this, but the buffer means that the way we have it set up here, this setup works if initial hydroxide is this. But what we have here is we have a buffer solution. And so the hydroxide initial is going to be about equal to the hydroxide at the end, at equilibrium. And so here, makes this problem a lot easier, because if we do iron 3 hydroxide, this is going to form iron 3 plus, right, plus 3 hydroxides. And we say that the initial is 9.12 times 10 to the minus 10 molar here. And the initial iron is 0.013 molar here. And then there's going to be a change, and then at equilibrium. At equilibrium, we're going to have 9.12 times 10 to the minus 10 molar. This is going to be buffered. So in reality, we lose it because we started with 10 to the minus 10 molar, and we end up with 10 to the minus 12 molar, so we consume some of our hydroxide, but the buffer is going to prevent that. Well, if the buffer prevents that, then that means that the iron 3 concentration here at equilibrium is going to be dictated by this, because this has to agree by KSP. And so actually the calculation is a bit easier, because the KSP is going to equal the iron 3 concentration at equilibrium times 9.12 times 10 to the minus 10 cubed. And that means the iron 3 concentration at equilibrium has got to be KSP 4 times 10 to the minus 38 divided by 9.12 times 10 to the minus 3 cubed, divided by 9 point, let's see, let me use parentheses here, 9.12 times 10 to the minus 10 cubed. It didn't work, sorry. Shoot. Did someone get it?
5.273 times 10 to the negative 11.
Okay, let's double check that to make sure that works. So let's check K. And so 5.27 times 10 to the negative 11 times 9.12 times 10 to the minus 10 cubed. So let's do that. 9.12 times 10 to the negative 10 cubed times the iron, 5.27 times 10 to the minus 11. Equals 3.99 times 10 to the minus 38. So this checks out. All right, and so this iron 3, because the solution's buffered, is going to come out 5.27 times 10 to the minus 11 molar. Because now, you know, we got a lot higher hydroxide concentration. If we started off with this hydroxide and we weren't replenishing it with a buffer, then the hydroxide would have gone to this and would have been precipitated. Over here, the hydroxide, yes, we're losing some hydroxide due to precipitation. And so what we can do is we can calculate the percent iron remaining. The percent iron 3 plus that remains is equal to 5.27 times 10 to the minus 11 divided by the original amount, 0.013 times 100%. And so we started off with this much in solution, we end up with this much in solution. And so that's going to be 5.27 times 10 to the minus 11 divided by 0.013 times 100. And so this is 4.05 times 10 to the minus 367 times 10 to the minus 7 percent remaining. All right, then we can calculate the percent iron 3 precipitated. Now the percent iron 3 that's precipitated is going to be 100% precipitation is 100 minus the amount that remains, so 0.123456405. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so this is going to be 99.9999595% precipitate. Okay, that's how much iron is going to precipitate out, okay, with this hydroxide. There's two ways of doing this problem. One way, remember when I said at versus in, you know? Do you guys recall that at all? Okay, I'm going to try to be clear, you know, is that the initial or is that the equilibrium? In this case, it was actually the equilibrium, the hydroxide concentration. And especially the buffer doesn't change.
And you said when you say something is at, then you're saying equilibrium.
Yeah, you just have to be careful. Yeah, when I say at, that means at equilibrium, but I'm going to add a few extra words to indicate. I'll say initially or at equilibrium or something like that. Okay. But for buffer, then you should know. For buffer, it's going to be both initial and equilibrium. Okay. What time is it now? 2:18. Okay, thanks. All right, any other questions? The chapter 18 test is coming up, right, Thursday. So if there are no other questions, then I need to move on.
from this. We could calculate how many grams precipitate. Because if we know the volume, let's say we had a liter or 500 milliliters, then we can figure out how many moles we lost, and then from the number of moles we lost, we can figure out how many grams precipitated. And so we can calculate the number of grams. Or, the other way of doing that is, if we know 99.9999 whatever percent precipitates, then we start off with 0.013 moles, we figure out how many grams that is, and then of this, and then we can figure out how many grams precipitate we get. Okay, so if there are no other questions, we're going to move on to chapter 14. Are there? No other? All right, chapter 14 deals with kinetics. Kinetics talks about the speed of reaction. And so what types of questions do we want to answer? We want to answer, how fast is it going? How fast? How long will it take? How long will it take for 95% reaction? How long will it take for the milk to spoil? This kind of stuff. How fast, how long?
So it's like a duration of time.
Yeah. And so initially we're going to do this empirically, And so we're going to do an empirical analysis first. Empirical, what does empirical stand for? Empirical stands for an empirical equation. Empirical equation means that the equation came from theory, or that the equation came from observations? Observations, yeah. So an empirical equation is an equation derived from observations. And we can use this equation to make predictions. And so what we're going to do is we're going to have to take some observations. So an example of this would be the crystal violet plus hydroxide. This is the only yield crystal violet hydroxide. And we're going to make a plot of this so we can see what's happening here. On the y-axis, we'll put the crystal violet concentration, which is proportional to the absorbance. On the x-axis, we'll put the time. And so what did it look like? Well, initially we had fairly high concentration of crystal violet, and then the concentration goes down as it reacts. But did it go down linearly, or did it go down non-linearly? Was it a curve or a straight line? Was it linear or non-linear? It was a curve? Okay. So it was a curve like this. So in empirical analysis, we want the equation of this curve. If we have this equation of the curve, then we can calculate, for example, how long does it take to do this? Well, in an empirical analysis like this, we don't always have to have the equation. Like, for example, do you know the equation of this curve? Probably not. And so what we could do is we could do other things. For example, we could just graph this and do graphical analysis. If we do a graphical analysis of this, then there's certain patterns. For example, if I want to see how long it takes 90%, we'll go 90% from the start, because we actually didn't start it here. We started it past there, but 90% from the start of data collection. And so if we consume 90%, that's like 9/10 of this. We go 9/10 of the way down, and this would be the amount of time. This would be the time required for 90% reaction, or 9/10 reaction. Right? And so we could do it graphically like this. One of these times is very important. One of these times is the time required to react 50% of it. The time required to react 50% is called T1 half. It's the time interval required. Some of these curves are interesting in that, sometimes we get a curve like this in which the T1 half have a pattern to it. And the pattern here is that, okay, we cut this in half, it takes this long. Now this is our new starting point. We cut it in half again, and we look how long it takes, and it takes the same period of time. So sometimes the T1 halves are, in each interval, are the same. And that helps us look at patterns in the curve. Sometimes they aren't the same. So for example, if this were a linear decay, I mean a linear type of consumption, what we'd see is that we'd see a different pattern in the T1 halves. So if this were linear like this, and just a straight line, then we look at how long it takes for the first. This is T1 half here. And then we cut it in half again. So the second time we consume half of it, it takes a little less. And the third time, it takes a little less. And so when we look at this carefully, what happens is if we have a linear curve, then the first T1 half is twice as big as the next one, which is twice as big as the next one. And so each successive T1 half gets cut in half. These are the types of things that we do when we analyze these types of curves. We try to figure out, what are the patterns that we can see in here, and what types of connections can we make. Now, one of the things, this is if linear, but different kind of pattern. One of the things we're going to look at is something called the rate of reaction. Now the rate of reaction is going to equal the change in the crystal violet concentration divided by the change in time. Now, this is just delta y over delta x. Y is the crystal violet, x is the time. And in other words, this is a slope. So the slope of this is negative. If it's negative, we put absolute values, because the rate should always be positive, whether we're gaining it or whether we're losing it, because you might say, okay, 5 grams per hour are lost in this reaction. Well, you would never say negative 5 grams are reacted, because there's no such thing as negative 5 grams. And so we put this as an absolute value here. Sometimes it's positive, sometimes it's negative. But the rate is always positive. Now, we have different rates on this, depending on where we map it out. Like, for example, here, if you look at the slope right at time 0, so we'll call time 0 here. If you look at the slope right at time 0, then the easiest way to determine the slope right at time 0 is try to draw a tangent line like this. Then we'll get our delta y over delta x. And this slope here, the slope of the tangent line, actually the absolute value of the slope, this is going to be slope of the tangent at t0 is equal to the initial rate. And so you can see that the initial rate starts off very fast and it reacts quite quickly, but as time progresses, the rate, that is the slope, flattens out and things start to slow down. And so, this last little bit of percentage for the reaction is going to take quite a lot of time. If less than 5% reaction has occurred, then what you can do is you can take the first 2 data points, like this, and then just connect them with a line here. So we'll do that here. And then we'll get the slope. So the first 2 data points would be, let's say, T0 and T1. The slope here, this is called the average rate over the time interval. T0 to T1. And if we have less than 5% reaction, then this is about equal to the initial rate. And so what we could do is we could just draw a line connecting the first 2 points like this. Oops, I'm off a little bit. We connect the first 2 data points here, and if there's less than 5% reaction, well, the error is not going to be huge. You know, it's just going to be off a little bit because technically the initial rate is the tangent over here. So, you know, if we drew the tangent line here, that would be it. And so it's going to be slightly off, but if there's less than 5%, that error is acceptable. The actual curve, you know, the problem is it's because the slope is always changing. So the actual curve looks something like this. You know? Where's the curve? Let's see what time it is now. 2:30. All right, so we have a couple more things. We don't have to do the average right at the beginning. We can get the average rate anywhere. So if we connect these 2 dots here, then determine the slope. This would be the average rate between these points here. And we can also do a tangent line anywhere on this curve. And the tangent line, the slope, actually the absolute value of the slope of the tangent is what we call the instantaneous rate. And the instantaneous rate at time 0 is the initial rate. But we can get the instantaneous rate at any time on this curve. And so if we look at these 2 points, the instantaneous rate right at the start of that time interval is here.
It's really late.
Ooh, that's right, 2:25. Okay, sorry.